My day is going great. Just if we can figure out the sound issue.
Yeah.
Oh, I see that I'm moving.
Like, turn
The sound meter is moving. That's good, right?
Yeah.
Okay. Quick question. I see that you have my slides up. Are those the slides I uploaded in the Dropbox?
Yeah, I think he is.
Yeah.
Let me try share screen here.
Okay, but I can hear. Is there any way that I can share my slides from my computer right now? Because I think I made some changes to the slides since then, or I can upload them again in the Dropbox real quick.
So that's the other presenter. Let me see what's happening here. Right. That's yes. Also here.
Okay, let's try now. Check sound, check sound. Okay, doesn't sound like I hear myself talk, so that's good.
We have the room here turned off. Do we have to turn that off in order to hear?
Endless void. What we might have to do is we'll have to mute the podium mic in order for us to hear him.
Okay.
Sure. Hello, my name is Alexis Berg. I'm an assistant professor at the University of Montreal in geography, etc., etc. Oh, okay. Hey, Matt, maybe can you say just a couple of words in the microphone in the room so I can see if I hear them in the live stream? Okay, good morning, everyone. I hope you can hear me all right. My name is Alexi Berg. I'm an assistant professor of Earth System Science in the Geography Department at the University of Montreal. I apologize for not being here in person today as initially planned, having some health issues that kept me from traveling. What I'm going to be showing today is mostly the work of my student, Juliette Goulet. Her master's project in partnership with people at Uranos, mostly Olivier Asselin. So all the credit for this work and these slides actually should go to her. And what we're going to be talking about today is the impact of climate change and land use change on the land water cycle over North America from regional climate model simulations. So yes, we're interested in this question that's pretty central in hydrology, pretty fundamental of the respective impacts on the land, sort of large-scale land water cycle of, on the one hand, climate change, greenhouse gas emissions that are driving climate warming and climate change that we know affect the land water cycle in a number of ways: precipitation, evaporation, infiltration, and so on. But also, on the other hand, from changes in land surface characteristics driven by changes in vegetation in the context of human-driven land use change, changes that also cause, we know, changes in evaporation, infiltration, runoff, etc. So we want to sort of compare those two effects in the context of man-made climate change. Like I said, this is a pretty central question in hydrology that we're not the first ones to look at. There's been many studies on the question. Modeling is a convenient approach to look at this because it allows us to separate those driving effects, those forcings. And there's a number of modeling tools that you can use to look at this question: global hydrological models, climate models, etc. And here we argue that regional climate models are actually interesting tools to use to investigate these questions. Because on the one hand, they do include the sort of land-atmosphere coupling part of the system that is important for these studies that look at land use change effects, because when you change the surface, there's also some feedback on the atmosphere that you need to account for. And compared to global climate models that a lot of people have used in previous studies to look at sort of large-scale hydrological changes, regional models have finer resolution. Obviously, that is important to look at more regional effects if that's what you're interested in. Interestingly, there seems to not have been a strong focus on land use change effects in most RCM studies to date. And so this work is in the context of the Lucas project that aims to look at land use change effects in RCM simulations a little bit more closely. So here we're going to use a set of simulations produced by Uranos in the context of that project that allow us to separate and compare those greenhouse gas emissions and land use change effects. So we have the following setup. Basically, we have the regional North American Cortex domain here on the left. The model we use is CRCM5, so the Canadian Regional Climate Model coupled to the Canadian Land Surface Scheme class for the land part. Resolution is nearly 1/10 of a degree. The large-scale conditions are from a sort of middle-of-the-road MPI, ESM climate change simulations. So we have a set of simulations, as you can see on the right, that basically are snapshot 30-year-long simulations for the present and the future, and we're basically changing land cover conditions and greenhouse gas conditions independently or in a combined way, so as to separate by comparing the relevant simulations the impact of greenhouse gas increase alone or land use change alone, right? For each simulation, we have 4 ensemble members, which allows us to sample a little bit of the internal variability in the system. And I should say we are comparing 2 different scenarios: SSP1, lower emissions, more of a mitigation scenario, and SSP3 with higher emissions and more warming. Right. So those 2 scenarios have different land use changes. So here are those land use changes in those 2 scenarios. So this is future minus present for SSP1 on the top row and SSP3 bottom row. Everywhere where it's purple, you're losing some of that vegetation type, and green, you're gaining that vegetation type. So here, obviously, those transitions are more complex than that in the 2 scenarios, but here they're translated to the corresponding vegetation types used by the land component of the model. So basically, the main transition happening in SSP1, where land use change is a little bit more spatially extensive than in SSP3, is that you're converting grasses on the right to broadleaf trees on the left, and also a little bit of crops in the middle, right? Versus in SSP3, what you see is that you're basically deforesting the eastern part of the continent and replacing it with crops. if you look at the left-hand panel and the middle panel. So these are the two main transitions if you summarize what's going on for future land use change in those two scenarios. So let's look at some results now. So here I'm showing SSP1 on the left, SSP3 on the right, temperature change, evapotranspiration change, precipitation change, and runoff change from top to bottom. And here this is only looking at summer because I'm going to be comparing those effects to land use change effects in the next slide, and those are mostly going to be relevant when vegetation is growing, so in the summer. So basically what we find here, without going into too much detail, is the expected climate change pattern that exists, that has been found in many studies. So extensive warming, more pronounced in SSP3 obviously than SSP1. For water cycle changes, we find basically this dipole of western, like drying in the west and wettening in the east in precipitation that is reflected in changes in ET and runoff as well of the same sign. And basically those hydrological changes scale with the warming in each scenario. So they're more pronounced in SSP3. So this is more or less what you would expect. No surprises here. Now looking at this, so the land use change effects in the same simulation. So again, SSP1 on the left, SSP3 on the right. We find that impacts are a little bit more subdued and more regional, or at least more co-localized with the regions of land use change in each scenario. As a reminder, I've included the main land use transitions in each scenario on the lower right. So grass to trees in SSP1 and trees to crops in SSP3. And the way to look at these maps is to start maybe from the second row, the change in evapotranspiration. So you have an increase in evapotranspiration in green. That leads to surface cooling in the summer on the top row, so up to maybe 1 degree Celsius locally of cooling. Also leads to increase in precipitation, sort of positive feedback on the atmosphere on rainfall. And if you look at the bottom row for surface runoff change, find a picture is a little bit more complicated, but at least more negative changes compared to the effect of greenhouse gas emissions in the previous slide. Obviously here things are not scaling according to, there's no scaling according to the scenario. There's just different regions affected by those land use transitions. So impacts are, to sort of summarize these effects and compare them, we're going to look at regional averages over the red domain here. If you look at the second row, the red box, the eastern part of the continent, where we have substantial land use change effects in sort of both simulations. And if we do that, we find the following histograms. So on these histograms, you have SSP1 on the left, SSP3 on the right, greenhouse gas effects on the top, and land use change effects on the bottom row. These are changes future minus present, and light blue is precipitation, green is evapotranspiration, runoff is dark blue. And on the left-hand side, on the left of the dotted line, you have the annual averages and the seasonal averages on the right. Basically, what you find is that over that region, at least, greenhouse gas emissions and the associated warming linked to an increase in all three fluxes, precipitation, evapotranspiration, runoff, that are basically amplified, as I was saying, in SSP3 compared to SSP1. And the ensemble members, show some consistency in that response. So it's not just noise. And if we look at land use change effects, the contrast is that it leads to an increase in evapotranspiration, again, a small increase in precipitation, and a decrease, change of opposite sign and runoff, pretty consistently across seasons, actually. In contrast to climate change, the impacts of land use change are similar in SSP1 and SSP3, so that they're sort of comparable to land use change, to greenhouse gas emissions in the SSP1 scenario. If you look at, for instance, ET in the summer, JJ8, the green bar, obviously in SSP3, the impacts of greenhouse gas emissions dominate. And finally, if we try to understand what processes are causing these changes, in terms of those land use change effects, what I'm showing here are the changes in land surface characteristics caused by these changes in vegetation. So on the left, you have the change in annual evapotranspiration as a reminder. So we're over the eastern part of the domain again, that is used on the histograms on the previous slide. So SSP1 at the top, SSP3 at the bottom, and changes in minimum stomatal resistance, root depth, LI, maximum LAI used by the model, and surface roughness length. And basically what we take from these changes, which are driven by changes in vegetation types again, is that in both SSP1 and SSP3, the land use change induced increase in evapotranspiration is dominated by the decrease on the left hand side of the right panels, the decrease in minimum stomatal resistance, basically because in the model, crops have lower stomatal resistance than trees. That resistance is lowest in crops, lower than trees, lower than grass. So that in SSP1, when you move from grass to trees, you're decreasing stomatal resistance. And SSP3, when you're moving again from trees to crops, you're also decreasing stomatal resistance. So that leads to that allows ET to increase in both scenarios, even though the transitions are different. Sorry, the transitions are different nature. The other parameters here, it's a little bit more complicated, but they would actually not explain the ET response that we see because they mostly play in the opposite direction. That would actually lead to a decrease in ET. For instance, a decrease in root depth or a decrease in maximum LAI would not cause the increase in ET that we see. So that's our interpretation of those simulations for now. So basically, if I try to summarize, RCM simulations indicate that future land use change causes substantial regional hydrological changes over North America, mostly an increase in ET that leads to an increase in precipitation through land-atmosphere coupling, and a decrease, importantly, in runoff, surface runoff. We find that we have similar sign impacts in SSP1 and SSP3 despite different land use transitions. And the same effect linked to stomatal resistance changes in the models is driving those responses. And if we try to compare both land use change and greenhouse gases effects, basically in the SSP1 mitigation scenario, we have more extensive land use change and more modest greenhouse gas emissions, so impacts are more comparable in magnitude in terms of impacts on the water cycle. In SSP3, obviously, the greenhouse gas effects dominates the response, even though land use change has some strong but more localized effects where you have strong deforestation. Lastly, I want to say that these are preliminary results. We just started looking at these simulations, so if you're interested in those, please don't hesitate to reach out. And I want to acknowledge our founding partners, CERC and MyTax, for this work. Thank you so much.
Does anyone have any questions for Alexis Berg?
Hello? I can say there's a question about the...
Here for you, for the audience, and here for the... Okay, great. Thanks, Alexis. Appreciate that presentation. I'm just curious to know your how much confidence you have in your runoff results, like how class are you representing in your representation of the model, the hydrological processes? I'm thinking of the lateral stream flow and hill slope hydrology processes in the model, and how that might impact your results for the runoff component.
Sure, thanks. Can you still hear me? I'm going to go ahead and answer the question. Yeah, basically, I'm not familiar with the class. Just recently started working with these simulations and actually working with the Canadian modeling framework. I would say that obviously the runoff answer is always a lot of uncertainty in land surface processes to generate runoff in particular. But on some level, there's the macro scale budget response. If you increase ET and you increase precipitation a little bit less, from sort of a water budget perspective, you're going to have to use water somewhere else, and that's mostly going to be at the expense of runoff. So I think there's some sort of water budget constraints. Obviously, there's a lot of wiggle room with other variables like soil moisture and all these things. that we haven't really investigated so far. But yeah, I think there's a water budget constraint here that's causing a decrease in runoff in those simulations. That's how I think about it, at least.
Any other questions? Yeah, thanks.
So thanks, great for that. The next presentation is from Yoandi Alonso. Great, while we get that up, so Yoandi will be talking about projected changes in wind speed and cloud fraction over Quebec using high-resolution climate models. So.
Okay. Hello, everyone. My name is Yoandi Alonso. I'm a postdoc student from the University of Montreal under the supervision of Professor James King and with the collaboration of Helen Cote and Biliana from Uranus. Today, we're going to talk about a little bit about the projected changes in wind speed and total core fraction over Quebec using the high-resolution climate models. Like we know, climate models are essential tool for understanding and projecting regional climate processes such as surface, winds, and clouds cover. The majority of the studies have been in using global models in global scales, but particularly in our study domain, the Quebec province, there are just a few results in these variables. So the high-resolution models should be expected to improve the representation of wind and cloud processes. But however, there are just few work related with that. For this reason, the objective of today's work is to assess the robustness of simulated changes in wind speed and total core fraction using the high-resolution climate models like North American Cortex under the climate future scenarios RCP 4.5 and RCP 8.5. So the methodology we use, first of all, we have an ensemble of a set of ECMs for historical period from 1980 until 2010, and for future projections until 2010, from 2010 until 2100. For both climatic scenarios, the resolution of these Earth system models are 100 kilometers, and we have also two ensembles of the North American Cortex models, 44 with the resolution of 50 kilometers approximately, and North American 22 with 25 kilometers of resolution. These regional climate models are driving using the same ECMs that we use. Going further in the analysis, we're going to analyze as well the trends in the wind speed and clouds using 4 locations of the meteorological station, one in the north, which is Cujuara Peak, Cujuac in the east of the province. In the south, we have Pierre-Trudeau in Montreal, and in the east we have Gaspé Station. We use the methodology from the IPCC, which has 3 approaches. The first one, with the solid colors, we will be representing the robust changes in the robust signals in the climate change. With the reverse diagonal, we have the no change or no signals, and with crosses lines, we have the conflicting signals between the different models. So how robust are future wind speed changes? First of all, we have the simulated wind speed vertical pressure levels from surface until 200 millibars. In the first column, we have the historical model outputs, and the second column, the future output from 2071 until 2100. And we have the third and fourth, the absolute changes between both future and historical periods. The first panel, the RCP 4.5, and the second one, the RCP 8.5. That we can see, we found in every map the diagonal lines that represent that there is no robust signal of change, except for a very small spot in the ECM for 200 millibars. So going to the surface wind, we have the same ECM for annual, but we have the 44 North American cortex ensemble and the 22 North American cortex ensembles. We see that there is no change, but in the same analysis, but the different seasons, still being no change. But North American 44 and North American 22 projected wind speed changes in summer and autumn. There is changes, but no robust signals of change in the wind speed. So for the RCP 8.5, the same analysis that before, no significant changes. And during the different seasonals, we have no signal of change, but again, we have the larger seasonal changes in surface wind speed in the northern part of Quebec specifically, than summer and autumn. Going a little bit deeper in the analysis, we have these 4 stations in the north, in the south, in the east, and in the west, and in the east. And we can see that the gray colors are the historical trends, and the future projections are with the blue, the RCP 4.5, and in red, the spread of the models in the RCP 8.5. We see that the slopes are positive during the station located in the north, which are in agreement with the results that show before. So how robust are future changes in total curve fraction this time? We see the same analysis again, the same methodology compares with the annual of the 3 different resolution models, the ECMs, the North American Cortex 44 and North American Cortex 22, down the climate future scenario 4.5. So there is not robust change, neither for RCP 4.5 for clouds, and the larger seasonal changes are presented this time during winter and spring, and again, no robust signal of change needed. For the RCP 8.5, or a relative change of total curve fraction, we see in this case that the story is different. We have, for ECMs, no change, no signal of robust change, but for RCP 4.4, for the RCP North American of resolution of 50 kilometers, we see that there is significant change in the province of Quebec, and even better represented for the North American 22 Cortex simulations. So this highlights the importance of using multiple resolution ensembles for storing this kind of variable. So winter shows the largest increase, exceeding up to 25 of total curve fraction, while summer present the area of decrease. But in the case of summer, there is not agreement in this kind of models. For the annual total curve fraction trends, the same 4 stations, we see that the slopes still positive for Kujuara Peak, and there is more wide spread of the total curve fraction compared with the stations located in the south and in the east. So for all in all, there is no robust changes in wind speed are found about the surface, except at 200 millibars over the northern Quebec under RCP 8.5. At surface level, wind speed projections shows the robust signal, but mean ensemble changes are most pronounced in summer and autumn over North Quebec, up to 45%, in high-resolution RCP 8.5 simulations. Under RCP 8.5, robust changes in total curve fraction emerge in both the North American Cortex 22 and North American Cortex 44 simulations, reaching up to 25% in winter. However, no such changes are detected in coarser resolution Earth system models. This highlights the importance of high-resolution modeling, capturing regional cloud processes often ignored by global models. Thank you very much.
Any questions?
Thanks, Yoandi, for the clear presentation. My question is, do you plan to assess changes in maybe wind speed extremes instead of just the means, or is that future work?
That is an interesting point, but like we are working in a project with contamination, with pollution. I'm in charge of the wind speed and clouds. We are not very interested for now in this extremes because we are currently working in the direction and the mean wind speed, which is for the transportation of the pollution. But maybe in future projects, I will be very interested in using this kind of extreme winds. Yeah, for sure.
Hi, Yoandi. Great presentation.
Thank
Just
you.
a quick question, because you pointed out at the end towards the importance of a high resolution for resolving like some cloud dynamic and stuff. And I was just wondering if this is something you're working on now on increasing resolution of your product, or you're looking into it. Just if you have something to comment on that. Yes.
Yeah, we are working on that. The idea is to still working in more ensembles. Like you see, we are using CMF5, the RCP series, 8.5, 4.5. But I'm currently working in the new CMX6 series, the SSPs. So the idea is to have the same result, the same analysis, following the same methodology, but with the larger ensemble and also with the new climate future scenarios. Okay, thank you very much.
Thank you very much, Yoandi. So our next talk is from Charles Ballantyne, who will be talking about evaluation of the growing season, soil moisture evapotranspiration relationship in the soil vegetation and snow land surface model.
Cool, thank you. Okay, hello everybody. So today I'm going to be presenting my PhD research on the evaluation of the growing season soil moisture evapotranspiration relationship in the soil vegetation and snow, or SVS, land surface model. I'm working on this research at the University of Guelph with my supervisor, Aaron Berg, and our collaborator at Environment and Climate Change Canada, Marco Carrera. And I don't have the logo up there, but this research is funded by NSERC. So off the bat, I'd just like to say thank you to them for funding this work. So first a little bit of background. Why do we care so much about evapotranspiration in land surface models? And what is evapotranspiration? It's the sum of moisture transferred from the surface to the atmosphere via a combination of evapotranspiration and via a combination of evaporation and transpiration. In addition to moisture, it also transfers energy to the surface through the latent heat of evaporation. So it represents a flux of both moisture and energy. As you can probably guess, this has a huge influence on atmospheric behavior. For example, higher rates of evapotranspiration tend to produce earlier and harder precipitation. So when we're talking about evapotranspiration in land surface models, we're really concerned about where and when and how much is happening, so we can easier predict stuff like storms. It has two distinct regimes. So it's either soil moisture dominated, where the supply of evapotranspiration is controlled by limited by the availability of soil moisture, or energy control regimes where the rate of evapotranspiration is controlled by the availability of energy in the environment. So we have lots of soil moisture, plenty of soil moisture availability, so it's kind of evapotranspiration is uncoupled from the actual soil and controlled more by stuff like plant characteristics and available energy coming into the surface. So the SVS model is a land surface model which simulates fluxes of energy and moisture between components of the land surface and atmosphere. And this is a land surface component set to replace the current land surface component of Environment and Climate Change Canada's weather prediction system at some point in the near future. And it's currently being used in their hydrological prediction system. However, this is a fairly new model. Development has only kind of happened in the last 5 or 10 years or so. So evapotranspiration is not, and soil moisture are not particularly well tied to observational data. There's been some studies on it, but we haven't really done a deep dive into it. So that's what we're trying to do here. So our objectives here are just to assess the representation of evapotranspiration and its relationship to soil moisture in SVS, as compared to our in situ lysomer data that we have recorded at the University of Guelph. So a bit of background on the methods and the data we're collecting for this. In 2016, 18 weighing lysomers were installed at the University of Guelph's Elora Research Station. These were designed to measure the entire water balance of both the soil and overlying vegetation. They're really high sensitivity instruments that can give you a really accurate view of what's happening with the entire water budget. They're pretty great. We have 9 with a silt loam soil and 9 with a more sandy loam soil. So we also have 2 different soil types, so we can kind of compare and contrast and see how the model performs for each. And we also collect data for a variety of crop types. So we cycle through winter wheat, soybean, and corn on about a 3-year rotation. This data can help us determine how well SVS is representing true evapotranspiration and true soil moisture behavior at this site. So what we did was we ran SVS in point form using meteorological forcing data from the ECCC Elora's weather station at Elora. Daily values of evapotranspiration and soil moisture outputs were compared to our lysomer data over the growing season, so April to October. We took some model stats, so our Pearson correlation coefficient, RMSE, and an exhibit agreement were calculated for each year and by each individual soil type, because we kind of wanted to see how well the model performed for different soil types, if that was a factor in model performance. And then we also calculate evaporative evaporative fraction and soil moisture relationships. Were calculated and compared. And I'll talk a little bit more about that and what that means when we get to that slide. But essentially, it's a measure of the actual land-atmosphere coupling strength at the site in our actual data versus our model. So here are our results for evapotranspiration. Our best performing year for evapotranspiration for both soil types was 2020, with an RMSE of about 1.63 in loam and 1.48 in sand. And our worst performing year for both soil types was 2021, with an RMSE of 2.37 in loam and 1.97 in sand. And sort of the standout points here was that for both the best and worst performing years, we saw dips in performance at different times in the season. So for our best performing year, we kind of saw it at the end after harvest and senescence. And for our worst performing year, we saw it more during the late growing season in kind of August there. And we're not really sure why that's happening yet. It might have to do with the plant types being planted in those individual years. It might just have to do with something about the meteorology. We would love to dig a bit further into that, though, because it's kind of an interesting result that points to some nuances in our sort of ground data that SVS isn't handling particularly well. For soil moisture, we had simulations for soil moisture and observations for the 5, 10, 30, 60, and 90 centimeter layers. But we focused on the 10 centimeter layer because we found that had the best relationship with evapotranspiration, which is also kind of interesting as an aside for when we're talking about like root zone, sort of plant relationships, where plants are drawing most of the moisture from. We found for this it was kind of in the 10 centimeter layer, so top layer. So this plot shows the time series for 10 centimeter soil moisture for the best performing year, 2017, and the worst performing year, 2022. So similar to for evapotranspiration, SVS had a tendency to underestimate soil moisture, and this underestimation was greater in sandy soils than it was, greater in loamy soils than it was in sandy soils. And our theory for why that is sandy soils tend to drain quicker. So, they tend to have lower soil moisture. So even though we calibrate SVS for each individual soil type for different runs, that variable doesn't appear to actually have much of a effect. So that's an important thing to note. And again, we see sort of like underestimations occurring at different times of the year, especially in the earlier season and sometimes in the later season as well. Okay, so this is our evaporative fraction results. So in order to assess the relationship between soil moisture and evapotranspiration, we calculated the evaporative fraction and soil moisture relationship. So we have soil moisture percentage on the x-axis there and evaporative fraction on the y-axis there. And the evaporative fraction is essentially the ratio between latent and sensible heat. And a higher evaporative fraction means a higher ratio of latent heat, which means evapotranspiration is contributing more to sort of the energy available in the environment, so higher evapotranspiration. And this also means higher land surface coupling. So as you can see here, this relationship is quite different between the model and the observations. So the observations are in blue there, and the model values are in yellow. And in evapotranspiration or evaporative fraction, in our observations, there's very, very low coupling. You can kind of see a bit of a relationship at really low soil moistures for both sand and loam, but it's pretty weak. And also the maximum evaporative fraction we're reaching in the observations is a lot lower than the model data. So really the takeaway from this slide is that land atmosphere coupling is a lot stronger in SVS than it is in our actual observations. So SVS seems to be overestimating land surface coupling strength. Finally, we want to take a quick look at how well SVS is representing soil moisture down the sort of vertical soil column, because it didn't seem to be doing a good job. And the results here, this is just averaged mean soil moisture at each layer. We had observations and modeled values for over the year. So again, SVS is in yellow. Lysomer data is in blue for both loam and sand, and then the standard deviations and the dashed lines there. And as you can see, SVS is really just kind of representing a homogeneous column compared to our like similar data, and that sort of underestimation of variability is really especially bad in loam. So we're just SVS is just draining water really, really quickly compared to observations. So our conclusions here, soil moisture and evapotranspiration are highly underestimated in SVS. Dry down is occurring a lot quicker in SVS than in observations, soil moisture dry down. And it's generally just a lot flashier. We see a lot higher peaks and then like quicker decreases in soil moisture. Vertical soil moisture variability is underestimated. Underestimation is a lot more pronounced in loamy soils than in sandy soils. And finally, and I think most importantly, land atmosphere coupling is highly, highly overestimated. So what are the next steps? How do we sort of fix this? Well, soil moisture representation needs improvement, but because the soil moisture isn't really controlling a lot of evapotranspiration at this site, that's not kind of the only solution we can take towards improving representation of evapotranspiration and land atmosphere coupling at SVS. Yes, that's important, but there's also other work we need to be doing. So that's why we kind of want to focus on vegetation representation next. SVS uses a photosynthetic model to calculate evapotranspiration. It doesn't appear to be performing particularly well. So kind of digging into that, seeing if there's any alternatives we can throw into SVS to see if we see any improvement from that. We can improve either via tweaking model parameters or doing data assimilation, and we're kind of interested in doing data assimilation. But of course, before we start throwing data at the problem, we need to make sure it's actually representing the processes correctly, because just throwing out data at a problem where, you know, we don't really understand what's going on isn't a very good scientific process. So yeah, those are the next steps. Thank you for listening.
Questions?
Thank you, Charles, for your very impressive presentation. My name is Krushal. I'm from University of Alberta. So I have two questions. So first question is, I wanted to know how does evapotranspiration is calculated or simulated in the model?
Yeah, so it's using a photosynthetic module, the name of which is like just on the tip of my tongue right now. I can't quite remember, but it takes a variety of inputs. So it takes like LAI and a variety of like plant attributes to calculate. So like crop attributes, plant height, as well as surface roughness to calculate. Should have included a slide with the equation on it so I could show you.
I just wanted to like know if I use some kind of like Princely trailer or some kind of formula. Or like
Yeah, it's a formula-based one. Yeah. Yeah.
I see. And like my second question was like, how does evaporative index is calculated? Because I was curious that when you showed it's kind of overestimated from that. So I wanted to know how it's calculated. Is something to do with how it's calculated or something else?
You mean like the evaporative fraction?
Oh yeah, fraction.
Yeah. So that's just a simple ratio of latent to sensible heat.
Oh, I see.
Yeah, so it's just a ratio. Yeah, so like how much, you know, of the total heat in the environment is latent and how much is sensible heat.
Good. Thank you.
Yeah.
No question? Thanks.
Oh, yeah.
Thanks for the presentation, also very interesting. And I think I go back to the first question, how is calculated the evaporation? And I wonder whether you can fix one of the two errors, because you have errors in the soil moisture and you also have errors in how much you evaporate.
Yeah.
So it would be a good idea maybe to try to make new calculations by giving the model the right soil moisture and then calculating and try to see which one is at the bottom of the error?
Yeah, no, I think that'd be a really interesting approach. There's a previous study that's been done that used actually evapotranspiration as forcing data, and they didn't have as much soil moisture error. It was at a different site, but I thought that was kind of interesting, and that's definitely something we'll be kind of looking into going forward. So thanks.
Talking about soil moisture, what kind of apparatus do you use in your dosimeter to assess the soil moisture in there.
Sorry, can you just repeat that?
Oh, yeah. Talking about
Okay.
the assessment of soil moisture
Yeah.
in your setup, which sensors do you use?
I'm not entirely sure. I'm not like super familiar with sort of setup and stuff for the lysimeter data. Yeah, I
Okay.
usually rely on our,
Yeah.
the guy who does all that stuff to tell me
Yeah,
those
just
things.
as a comment is that so usually the sensors don't kind of directly measure the moisture constant. They measure like a different value, then transform them into what we want, and often the kind of default conversion curve on them is a little lacking.
Yeah.
And so in some aspect, I feel like if you were to find something a little better, maybe you could get your data to kind of match. a lot
Yeah,
more.
yeah, no, that's a really good point. Yeah, you always have to look out for like measurement and error and stuff, and that's also why I think the data simulation approach would be kind of interesting. Maybe for soil moisture, which isn't maybe our direct focus in our next sort of steps, but a future study. Because like data simulation will take into account like sensor error and stuff when it's making its like adjustments. So yeah, no, but that's a good point. Yeah,
Thank you.
Great. Yeah, thanks a lot.
Thank you.
Presenter.
You want the present?
Yes, please. Yeah, and I might have to click for an animation or two. So. Okay, perfect.
Is that okay then?
Yeah,
that's great. I'll just quickly introduce. Yeah. So our next talk is Noah Stanton. How does tropospheric VOC chemistry affect radiative forcing in pre-industrial climates? So,
yes, thank you very much for the introduction. Yep, I'm Noah Stanton. I'm coming out of York University, out of the supervision of Dr. Neil Tandon. And a little bit of a title change, but I'm going to be talking about how does explicit tropospheric VOC to SOA chemistry affect radiative forcing in pre-industrial climate. And I first want you to look at this animation, which is showing a % difference in secondary organic aerosol between two different chemistry configurations within the Community Earth System model version 2. And you can notice quite a dynamic change, and there seems to be some seasonal pattern to this difference. So what I'm trying to highlight here is clearly the choice of your chemical configuration for this VOC to SOA chemistry is impacting the output of these climate models. So to start, I'll just get into some of the background of the chemistry involved in this SOA formation. So biogenic volatile organic compounds, or BVOCs, are the predominant precursor to secondary organic aerosols. And there are also anthropogenic contributions of VOCs to the formation of SOA, but they are minor contributions. And I just have this little sort of scheme of the chemistry involved in SOA formation. So these biological volatile organic compounds are highly reactive species with atmospheric oxidants like hydroxyl, O3, NO3, and Cl. And they go through these reactions and can make intermediate volatile organic compounds, which have a lower volatility than that initial VOC. And eventually these can condense into SOA products or evaporate back out into these IVOCs. And so what this is really trying to show is there's a complex relationship between the gas phase chemistry and this aerosol chemistry. And this is even quite a big simplification of that. So how are you going, what sort of parameters do we want to look at when we're assessing the radiative differences? So I bring you to figure 2, which shows the observed contributions to warming or to the effective radiative forcing from a pre-industrial baseline to a modern climate in 2019. And as we all know, CO2 has had the biggest impact on this radiative forcing of about 2 watts per meter squared, with methane coming in a close second. We can also see VOCs are contributing to warming. And then on the cooling side, I'll just point to organic carbon. Secondary organic aerosols fall into this category of organic carbon. Although this VOC to SOA chemistry that I'm describing isn't just sort of impacting one of these constituents, it has a more broad effect on these constituents. But why are we assessing effective radiative forcing? So it's quite a commonly used metric, and it allows for apples to apples comparisons with other studies. And just as I was talking on that previous slide about how the modern climate is sort of the perturbed state, and then the control is that pre-industrial state. In our study, we're sort of flipping the script on that. We're saying that the more explicit representation of VOC to SOA chemistry is our perturbed state, and that is represented with the 1D volatile basis set. And then our control state is the one that implicitly describes this VOC to SOA chemistry using the SOA-G scheme. And I'll just bring you to figure 3, which is just showing the transfer of knowledge between laboratory and theoretical studies to observations, and then also to chemistry climate model studies. And we're sort of falling in between like the blue box and the red box, because we're trying to understand how these chemistry parameterizations impact the radiation outputs of these chemistry climate models. And it's a continued peeling of the onion from our previous work published in ACP under Stanton and Tan in 2023. So just to describe a little bit about the tool that I'm using in order to do this comparison, we're using the Community Earth System Model version 2, and you can see the 7 model components in the coupler in figure 4 on the left side of the slide. And we picked this because there's detailed chemistry climate interactions that we can capture with the whole atmosphere community climate model, which we've configured it in. And those interactions can be seen in figure 5. So now we'll just move on to the particular cases that we set up in order to do this analysis. So table 1 has all of the simulations we used in this study. I just want you to bring attention to the first letter in the case name. It's either W or M. And so the W is just standing for the whole atmosphere chemistry model. And this has detailed chemical modeling with 231 freely evolving species, detailed SOA modeling, and it uses the 1D volatile basis set. Now, the M cases, on the other hand, that stands for middle atmosphere only. So in these configurations, this VOC to SOA chemistry is, again, implicitly defined through this SOA-G scheme. And now I'll move to the second letter in the case names. It's either an F or a C. And so the F is standing for fixed sea surface temperature, or CI states. And fixing these SSTs allows us to do a calculation of ERF using the ERF FSST method, which is quite a standard method. But of course, by fixing these states, we don't get that full climate response. And so we also did additional coupled studies, and that's what that C, that second letter C, stands for. And these actually are an updated initialization from Stanton and Tan in 2023. So if you have any questions about the differences, feel free to ask in the question period or afterwards. And of course, with all of these simulations, external forcings and emissions are fixed to pre-industrial levels in a cyclical cycle, 12-month cycle. So yeah, let's just get into some of the results. So of course, first we look at, if you look at panel A, we're looking at the net radiation differences between this WF minus MF comparison. And if we take the global mean of this difference, we can get this ERF FSST value of about 0.49 watts per meter square. So of course, we want to know what are the drivers. Are these predominantly long wave drivers or short wave drivers? And it led us to look at the short wave differences, which of course, then if we want to further peel the onion of the short wave differences, we look at panel C, which is the net cloud short wave differences, and panel D, which is the net non-cloud short wave differences, which you can really think of as clear sky. And what we see with panel C is, yes, spatially, there is this connection to the net shortwave changes. But then when we look at the percent global mean difference, it's only about a 0.058 watt per meter squared difference. And then when we look at these net non-cloud shortwave differences, we actually see that they contribute the most to these shortwave differences. So of course, thinking non-cloud, so maybe aerosols are involved in the differences. And of course, SOA, we're talking about VOC to SOA modeling, right? So this led us to look at the aerosol optical depth differences between the two configurations. Again, this is the fixed SST comparison. And what we want you to notice is there is this visual similarity to the differences in the non-cloud shortwave. And if I can click on the slide, hopefully this animation works. Just sort of look over the Amazon. And let's see if it shows up. Oh, it didn't. So I can flick back to this, and you can just look at how the differences over the Amazon are opposite to the differences that we see in the AOD. And there's a similar pattern throughout the globe in this. And of course, talking about aerosol optical depth, we wanted to then look at the total aerosol column burden changes between the two configurations. And so that's what we're doing in panel B. And indeed, we do see a strong spatial correlation between the AOD changes and the ACB changes, as well as in the percent global mean difference. We see a similar order of magnitude of difference, with the AOD difference being about minus 4.9%, and the dry ACB differences being negative 5.1. And just to say, aerosols within CESM are separated into in-cloud or dry. So all of these comparisons are with the dry component of aerosol. So this next figure, figure 8, it's a 6-panel with all of the different aerosols that are represented within the model. I can talk about these details afterwards in the study because they're quite comprehensive. But the main 2 variables that I want you to be looking at, 2 panels, are panel B with the SOA changes, and then panel D with the dust changes, because they sort of describe some of the broader strokes of what's going on. When we look at the regional SOA changes, we can see big increases in SOA over typical higher production SOA regions like the Amazon, Southeast Asia, and over Central Africa. But in this percent global mean difference, we see pretty minor changes. Now, when we look at the dust changes, they're actually constituting a large portion of this overall ACB change at about 4.7%. And I should say all of these aerosol values are normalized to the MF climatology, to be clear. And now, though, when we look at our spatial comparison or spatial correlations between AOD and SOA versus AOD and dust, it's clear that AOD is more strongly spatially correlated to the SOA is more strongly correlated to these AOD changes than dust is. And of course, we're trying to think about why is that so. One of our current hypotheses is there is more mixing of SOA with all aerosols, which may lead to faster dry deposition rates. And of course, I wanted to take a look at this full climate response, because everything else that we've been looking at previously was the fixed sea surface temperature response. So we have our coupled comparison here with WC minus MC. And I'm going to bring your attention to panel A, which is the surface temperature differences. And we can see surface warming in many parts of the globe, excluding an area off of Eastern North America. And when we take the global mean of this surface temperature response, we see about a 0.397 Kelvin increase in temperature. And there are associated changes in daily precipitation, changes in the location, the ITCZ, and reductions in the percent global mean difference of total cloud fraction. And we also see changes to circulations, which is somewhat represented in panel D in the sea level pressure changes. And of course, we also tried to measure ERF using another method, which is the regression method, and we get a similar value of about 0.4055 watts per meter squared ERF due to the inclusion of this explicit VOC to SOA chemistry. So just to conclude, as I'm a little bit short on time, I'll probably just leave this conclusion slide up, but I'll just quickly say, we seem to have an increase of SOA production in the typical regions that would be associated with that. We think there's increased mixing of this SOA with other aerosols within the model, which leads them to drop out faster, leading to AOD changes and a reduction in downward shortwave radiation in the model. And this leads to about, with the 2 different methods of ERF calculation, about a 0.4 to 0.5 watt per meter squared ERF change, which is approximately 1/5 of that total contribution to ERF due to CO2. But yeah, this was mainly focusing on these dry changes, and we hope in the future to investigate the microphysical changes to clouds as well within the difference. So thank you very much. I'm open for questions now.
Any questions? I'll ask ask a question. So you used CESM. Is
Yes.
that the only model you could use for this? Are there other?
Yeah, from my understanding, it's the model that we're most easily to set up these comp sets, and also has more comprehensive chemistry in this comparison. Now, I think there definitely is an impetus for us to look at other models and see if we can do more of these comparisons. Because I'm sure we could.
Well, if there's no other questions, well, thank you.
Yeah, thank you very much.
Okay, so the last presenter is me. Again, my name is Matthew Toohey. I'm at the University of Saskatchewan, so for those of you who are first time to Saskatoon, welcome. Got a picture of the campus just across the river here on the first slide, so if you have a chance to cross over the University Bridge and take a look at the campus, encourage you to do that. It's quite beautiful. Physics building is right here within what we call the bowl, which is a nice part of campus there to see. So it's right next to the geology building where there's some dinosaur bones. Anyways, it's worth a walk if you've got some time. But yeah, I'm going to be talking about something a bit more programmatic rather than really about science. I'm going to talk about the collaborative platform for CanESM, what's going on with this program over the last year and in general. And I'm kind of a substitute for Paul Kushner, who is the PI of this project, but he's busy down in California running a kind of summer school over the next few weeks, and so he couldn't make it here today. And so I'm giving this presentation with a lot of input from him. So I really need to acknowledge that most of these slides are from him, and a lot of input from folks from Environment and Climate Change Canada, including Neil Swart and Clint Seinen, and then a number of other people who are working within CP4C, including students and postdocs. And I'll get to introducing them a little bit more as we go on. So I'm just going to give a quick introduction about what CP4C is, talk a little bit quickly about its structure, give you a couple of samples of science that's been supported by CP4C over the last year, and conclude. So first of all, CanESM. So this is a program that's centered around the Canadian Earth System model, which has been in development through its component parts since the 1970s. So it is a very important contribution to worldwide efforts to do climate modeling, as it's an independent contribution to the ESM effort. So if you look at different climate models around the world, a lot of them actually have a lot of shared components, whereas a lot of the Canadian ESM is independent from a lot of those other models. So it's really an important contribution to global work on the climate. Through using CanESM, CCCMA has contributed hundreds of thousands of years to simulation in CMIP archives, right? So a huge contribution. But up until recently, CanESM was really was only able to be run on the computers in Victoria, and so except for some very, very slight exceptions. So really, you almost physically needed to be in Victoria in order to run this CanESM. And so since about 2022, there's been a strong effort to try and open that up so that academics, different people around Canada could run this Canadian Earth System model and do science with it. And so CP4C is the academic community's research platform to use CanESM. And so it's a sponsored project, sort of a branch and arm of CMOS. We want to increase national capacity in Earth System model development, application, and analysis. I'll get to this. We want to connect and increased science related also to observation, so including the high altitude and water vapor and clouds project, which you may have heard about in other sessions. It's over the last few years has received funding, which is helping the effort. And we have terms under the Digital Research Alliance of Canada, which provides computational facilities. So our goal is to enhance the collaborative use of the Canadian Earth System model in a manner that reflects best practices in the use of ESMs in climate science. So that includes technical workflow, documentation, computer resources in order to do simulations. We want to enhance development of CanESM. So by broadening the user base, we can actually help the development by having more people using it, more people wanting features relevant to different types of research. And a simple and transparent support policy reflecting resources and requirements, internal and external to ECCC. So I'll talk just a little bit about the structure of CP4C. So there's a steering committee. So like I said, Paul Kushner from U of T is the director and really the main moving force here. We've got a program manager or project manager. We have good buy-in from people from ECCC. So that's led mostly by Neil Swart. Clint Seinen has been also really important to that effort, Jason Cole. And then a number of academic members to the steering committee, which I am one of. And we meet regularly to consider scientific and technical priorities, HR, computer resources, and just one of the important things is liaising with ECCC. We have a working group community which gets together on Zoom calls regularly as well. And so this is open to all, including students, postdocs, ECCC members. We've got a listserv and a Slack channel. And so we're really opening communication between people. So students, when they're just starting up, every couple of weeks, they can get together with a few experts and a few other students via a Zoom call, trade stories, trade problems, and hopefully get fixes relatively quickly. One of the big issues here is porting the CanESM model to the Digital Alliance computers. And so ECCC people have been essential in that and providing a lot of support when we do run into problems. But the implementation on the DROC machines is converging with what people are doing at ECCC. So they're actually changing some of the procedures that they're using on their computers to become more in line with what we're doing on the DROC computers with CP4C. So eventually we want to see good consistency there, which will cut down on the amount of work that's needed to run them in both places. The implementation includes a lot of robust testing, a runtime diagnostics browser, which is super useful. So when students get going with CanESM on the DROC machines, they can pretty quickly and easily get some feedback as to whether the simulations are working and producing the right kind of results. As I mentioned, there's a lot of documentation online already that can help, including some sort of quick start guides for running CanESM on the DROC machines. And also mention a sort of issues page on our GitLab server so that when people want new features, they want to be able to run a simulation that hasn't been run before, they post that as an issue, and then that'll be seen by the experts at ECCC, and they'll work on implementing and fixing or providing whatever is needed to do those simulations. So it's a nice streamlined kind of workflow that seems to be working well. We had a workshop just a little over a year ago with people participating from all across Canada. So this is kind of the list of participants and where they're coming from. So we can see really from coast to coast. We had some hubs in different centers. You'll see a lot of people at McGill, but also Saskatchewan and Toronto. So a number of users, again, including postdocs, students, faculty from across institutions in Canada. Mention it's also important to have clear policies about how the academics here are relating and working together with ECCC people, and so that's all documented and put into a policy document. I don't have tons of time because I want to still get you up to lunch a little bit early so you can beat the lines from the other sessions today. But I'll just mention a couple of examples of science that's been kind of facilitated by CP4C. And so Anson Chung, who's a student of Paul Kushner's, gets the gold star in being the first student to complete CanESM simulations outside of the ECCC firewall, so on the DRAC machines, using the CP4C platform. So he ran a number of simulations looking at nuclear winter simulations. So what happens if you have I mean, it's a little bit dire as an example, but looking at a scenario where there's a nuclear war creating huge fires, which puts black carbon into the atmosphere a large amount, and looking at the climate impact of that. And so here are a couple of plots showing with some different scenarios in terms of the amount of teragrams of black carbon that was put into the atmosphere, what impact that would have on surface temperatures in the global mean, and then kind of breaking down the impact, what's causing those surface temperatures in terms of radiative forcing or changes in shortwave radiation and changes in downwelling long-wave radiation at the surface. So starting to look into the mechanisms of how this kind of forcing from black carbon plays out in the Canadian North System model. Another example coming from colleagues out on the West Coast at SFU is looking at something that's a little bit related to some of the talks we saw earlier in this session. This is about sort of, well, maybe not land use change, but reforestation and looking at its impact on the water cycle in a sustainable reforestation scenario. So looking at making changes in forest amounts in our future simulations and what impact that would have on the water cycle. So these plots are showing soil moisture content at basically present day and in a future scenario where there has been a reforestation of areas along the east coast of North America and in Europe and in East Asia. I mentioned connections to observations. And so if you haven't heard about HAWK is the high altitude aerosols, water vapor and clouds Canadian mission, which is connected to the NASA's atmosphere observing system. So HAWK includes 3 Canadian instruments, one of which is planned to be flown on a NASA satellite. The other 2 will be flown on a Canadian satellite in a coordinated fashion. And they'll be measuring, as the name suggests, aerosols, water vapor, and clouds. Different members are working on already using CanESM to try and do some pre-studies to understand a bit better how HAWK will enable better science when it's launched and planned 2031. So for example, IV-TAN at McGill is looking at how measurements from the TICFIRE instrument, which is again one of those 3 instruments, will be measuring radiation in the far infrared, including over the Arctic, and looking at how that can improve our estimates of the cloud feedback at the high latitudes. So just to kind of wrap up, take-home messages here. So CP4C, this collaborative platform for CanESM, is making the Canadian Earth System model usable by a much wider community, allowing new science, benefiting education, training, and collaboration between the academic and government sectors. In the moment, we're kind of in a little bit of a blossoming stage. We're getting new resources, including a software engineer dedicated to the project. We have a new allocation from DRAC, which will allow much more to be done in the next years, with the continued support of both the academic sector and ECCC. So this is then just a call for anyone who's interested in this, who wants to maybe run CanESM in the future, to come and join our working group. So there's some contact information here. Of course, you can just email myself or Paul to get connected with this group. Yeah, and that's about it. So I'll take any questions.
Questions?
Thanks, Matthew, and I always congratulate Paul and for this work because I think it will benefit eventually academics. My question is, what is the biggest challenge to basically go ahead with a program like this? There are quite a few that I can think of. I mean, there is the technical part, and for example, having someone that will take care of the model and running in the Compute Canada. There is also a lot of work that has been done to make it open and collaborate with the wider community. So maybe there is also the need for a coordinator or something like that. And then the scientific question. So maybe can you mention what do you think are the biggest challenges to go ahead with this kind of programs?
Yeah, that's a really good question. And, it's hard for me to actually put my finger on what the biggest issue is. I think it's important, like those things that you mentioned are all essential to making this happen, right? So, this wouldn't, I don't think, have happened if it wasn't for Paul's energy and really pushing this and happening. Because as you say, there's a lot of kind of logistical, programmatical, political kind of things that need to be done in order to just even have this happen, right? We needed to have ECCC really support this and say, yeah, this is a good idea, because if we didn't have that, it wouldn't fly. On the other hand, it also, I don't think wouldn't work if we didn't have Neil and Clint and those people from ECCC who are putting in the time and the effort to actually port this to a new system to deal with the bugs that come up, because most of us, if not all of us on the academic side, aren't really equipped to be able to do that part of it. So yeah, it's really important, and I think it shows a good, kind of collaborative spirit that has happened here in order to have both sides of that equation working together to make this possible. Thanks for the question. Okay, so great session, everyone. I hope you enjoyed seeing a cross-section of what's happening with our system modeling across Canada, and hope to see you in future years. All right. Thanks to all the speakers. Thanks for being on time, all speakers. It was really great. Yeah, have a great rest of the day and time in Saskatoon. So one more round of applause for all speakers.